Well, welcome. I'm Bill Wake. We're here working on a new project today. It's called 10th. It's much less than a fourth, I guess, is my little pun there. But it's a programming language. We're going to implement it in assembly language using an interpreted technique. And well, let's get going and see what we need. Let me fix this sound first. Okay, so what's the idea? Well, I haven't done much setup, just a tiny bit. We're going to start by doing some assembly language, just trying to learn this as we go. We'll get a hello world working. I found one from the book I'm using, or somebody did a Mac version of the one in the book I'm using. We'll implement a minimal test framework and extend it as we go. We'll implement a threaded code interpreter for a subset of fourth, or some approximation of fourth. I'm not married to fourth. It's just, it'll be a good model for us. It's a stack-based language, and it's traditionally implemented with something like what we're doing. Then we're going to figure out hello world in our new language and implement a small test framework for our new language in, up a level from the assembly one, and then implement some small app, a game or a calculator. We'll probably mix and match these, do them as we go. It's all iterative as usual. Okay. If you need some resources or you'd like some, the starting points for fourth, there's a book called Starting Fourth and another one called Thinking Fourth. Those are both available free online. I got the links down on the bottom there. The other book I used a lot to understand implementation of this stuff is Threaded Interpretive Languages. I think it's from 81. So this is all old technology. And then last, Programming with 64-bit is ARM Assembly Language. Stephen Smith, that's the book I've been reading on 64-bit ARM, along with some web stuff. And this last link is the Hello World that he provided. I'm going to say a word about what's threaded code first, because it's probably, I don't think it's I don't know how popular a technique it is anymore. It's kind of cool. So let's take a look. Basically what you're going to do is you're going to have primitives or primaries written in machine code, assembly language in our case, and you're going to have secondaries, which are calls to either other secondaries or to primaries. And the primary is basically a chunk of machine code. The secondary is basically a list of the secondary, well, the primaries and secondaries to call. So it'll give us access to the whole language. And the way the way this is, at least one sense, it's threaded. Not so much the dictionary. We'll go more deep, but the reason it's threaded is because you're either working your way through a secondary, which is kind of this little block, and then connecting down to machine code or connecting to another secondary. It forms a tree, and I don't know how they chose threaded to mean that, but that's what it is. The next thing we'll have is a dictionary. So all the primaries, most of the primaries will be in the dictionary, the ones users want to use. And the dictionary is organized as a linked list. So if you just focus on the yellowy orange ones on the bottom there, that's sort of your initial dictionary of terms. And so if we ever, like when we're compiling the structure on the left, we'll have to go find, you make a procedure call, in effect. We have to find that word in the dictionary and plug in a reference to it. And then as we define new terms, we get to those blue ones up top. They'll be secondaries. I guess you could define new assembly ones, but I'm not gonna support an assembler in our secondaries. We'll just put those in the assembly code if we need to. But the new ones you define then go on the dictionary as well. And so if one references another, then it has access to what's in the header for it. All right. And then the last piece that'll come together is there's an interpreter that's going to be some assembly language code that knows how to either go call a primary or call a secondary and keep track of which step you're on and, move you along. All right. And that's enough of a taste to get started. I think we're unlikely to get that far today. We'll see. I don't know. I've consciously not let myself go down and program any assembly language or any of that kind of thing. So It'll just be what it is. Okay, let's see. I've got a directory set up, a license, a README, the Keynote file you just saw, and a to do. I don't know what I said in here. Not much. Okay, and then the to do. Let's open that. Okay, so hello world in assembler, write a simple xUnit, develop a primary routine, develop a secondary routine and interpreter. I mean, once we have that, we're kind of rolling. Okay, yeah, it's reverse Polish, it's stack based. So, um yeah, it takes a little doing. I mean, like the HP calculators from way back when were stack based, and they were kind of an obscure end of things. You had to know that if you want 3 plus 4, it's 3 4 plus. But it does have some nice characteristics for us that, it makes a language that doesn't need a lot of variables, and you don't have to keep track of all the, which variables are they in registers and are they in memory and where are they in all this. The answer is they're all on the stack. So, yeah, I don't. This is more of a toy from my perspective. It's a chance to work on assembly and practice writing an xUnit and work through a kind of a cool little data structure that language implementers have used. I know at least some compilers. Well, besides Forth, I know the old PDP-11 Fortran at one point was threaded code. I don't know if it stayed that way. But the nice thing with threaded code is it can be very compact, and it's often faster than like a basic or whatever equivalent kind of thing would be running. So it was attractive on the old, the original round of PCs, personal computers. That something that ran faster than basic was nice, and you didn't have to go into machine code. So kind of nice. All right. Well, and then let's see. I've Atom. I don't know what the right editor package is going to be for us here. And then some files. All right. Now, what I have though is this this S. Mist, the author of our M1 assembler book. Okay, somebody put together Hello World for ARM on the Mac. All right, and let's see. Well, okay. The way this is just a literal print hello world. Here's the hello world. I've used several assembly languages before, so I can muddle through, I think. We'll see. But anyway, let's read this one. So global start tells the linker to use this. We'll have to see how we link it. Align to is making sure that code or data starts aligned. Now, I don't know if 2 is 2 bytes, I think. A lot of stuff needs to be on 2-byte boundaries for the assembly language code on the Mac. At least they require 2-byte boundaries. And some stuff, the stack they actually do in 4-byte boundaries, so, or four word boundaries, I think. We'll have to see. Okay, so what we're going to do is make a system call, and you can see that here. All right, we're not calling Linux, we're calling Mac OS, but anyway, we're going to move a 1 into X0 because 1 is standard out. All right, so this is just the Unix level write call. So when you call print or printf in C, it's calling this down at the bottom level. All right, it adds buffering and the nice formatting and stuff. Okay, so argument 1 goes in X0 as register 0. The next argument goes in X1 is hello world, points down to this label, and that's the string. Then we put the length of the string, 5 for hello, 5 for world, a space, a bang, a new line. Okay, so 13 characters. And then the system call. X16 is the register they used for the system call. So we're choosing system call number 4, which is right. And SVZ0 says call the operating system function, basically. When we get back, we have to make another call. So we move 0 as a return code for our program. And then we say, I'm going to call service 1. Well, that's exit. And then we make the service call. I don't know what this 0 does anything, but it terminates. All right, so let's take this. Now if everything's right for us, I think they do S. Yeah, so let's make a hello world.s. We'll put that in. We'll make a makefile, and we'll see if we can build this thing. Oh, where did I leave that? Here it is. Okay. I don't know if I can open a project. Add a project folder. And we're in desktop Twitch 10th. Oh, good. Okay. Make a new file. Paste that stuff in. We'll save it as hello world.s. Yeah, I think, well, yeah, I mean, ARM64 uses 32-bit instructions, 4 bytes, even though it's mostly manipulating 64-bit stuff. I think the claim was it does not work on misaligned. But yeah, that's a very common thing to require that your, instructions come on even words or stuff like that, but we'll see. Okay, so there's hello world. Let's make another one. Our make file, and they gave us a demo of that. Now, the thing with make files, I think these have to be a single space, and that's a tab. I don't know if this will work with tabs. Oh no, it's multiple spaces. We'll give it a try. No, this one can't be right. Let's see. Oh, there we go. xCrun is, I believe that's getting us the assembler. We're saying ARM64. L system, L is for library, so we're getting a system library. I believe I read somewhere you can't build without that, even though you don't really use it. So, kind of sucks. All right, so we take whatever's running out of this. Oh, yeah, we're getting the path. And then this, okay, so to build hello world, the first thing in the file, you need the object file. To get the object file, you take the assembler file. What do? You call assembler -o hello world.o, that's the output, and hello world.s. Okay. And I don't remember if it's capital M makefile or do they care? No, well, we'll use lower. All right, let me put this into a name. Makefile. Okay. Well, and then I don't know quite how to lay my windows out over here, so let's quit. Okay. Does this have a runner? I guess it'd be window or view. Console. Okay, that's promising. Not encouraging. A console I can't write to is not super helpful. Okay. Well, we'll just say make and see what happens. Missing sep. All right, let's see if that's really this. Although, actually, I think this maybe should be one line. Whoops, not VI. All right, let's try again. Oops. Okay, we're closing you. Oh. All right. Gosh, I haven't used makefiles in so long. Missing separator. That would seem to be on the makefile. Oops. Um, Whoops. All right. So makefile. You write a file called makefile. Yes. Okay, well, I can rename it. You always make -d. Okay, let's do that. -n's nice too. Okay, missing separators, line 2. I wonder, I'm just thinking if there's a weird space because it came from a web page. Notice that E start there, that's our entry point. I wonder what happens if I move this to... Missing separator. Maybe I do have to use tabs. Yeah, no, there's something screwy in the makefile. Others have had this. Oh, it require a tab. Okay, yeah, that could be it. Do I get a real tab? Yes. I think there was an interview with Stu Feldman, I think was the inventor of Make, and they asked him if he had any improvements he wanted to make, and it's like, no, I shouldn't have used tab. I'm like, okay. We'll do them all. Okay, so yeah, a lot of rules kicking in there. All right. Let's do make again. We'll just get our stuff. Okay, built for newer macOS than the one being linked. 11. I don't think I need to mention this. And that's version 11. Well, let's just say 14 and see if that makes it happy. Oh, he didn't rename. Oops, darn it. Oh, it did pick up the rename. Okay. Make again. Make clean. Okay, we got some work to do. Let's see. We must have an O. Yeah. RM start out O. Make. Okay, everything's happy. Oh, has been renamed to Mac OS version man. Okay. You can also do touch. Oops, if you can type. Okay, because make goes by the dates, the timestamp of the last change. So if it sees the object file is newer than the source file, then it's happy, and if not, it's not. Okay, so -O says hello world, so I should be able to say dot hello world. Again, I have to spell. All right. Okay. We're cooking. Okay. We clearly have some ways to go. So we can do clean. Well, whatever you have first is the target. So let's do clean. Doesn't depend on anything, but we'll remove star.o. Okay. Oh, I'm going to do VI all day. Okay. Let's see. So we should be able to say make clean. Okay. And then make should make something. And then dot hello world. All right. Okay. First I'm going to do some, well, no, we should check this in. This is a big step, right? Hello world says I can do everything. I guess I can say got. And hopefully this will push. Good. Alrighty. So Adam, I guess that's my question. Oh, you have to get a plug-in. Okay. What do we have to do? Open settings. No, I should pay more attention. Install. I'm not seeing that. Surely some of these. No, good diff. I don't need these languages. see a terminal on there. That's still the same. Oh, 84 total. Okay. Install. Now I search for this. Failed. Okay, let's just try terminal. That looks like a bug in Atom. I haven't updated this for a while. Okay. Maybe not the best choice. Let me see what else I have. So many old apps lying around. No, I think Adam's a little better than TextMate. I had, what was that one? It starts with M. Oh, do I have it on my bar here? That's Adam. Apache NetBeans. Haven't used that in years. Okay, I don't see anything better. I'm just blanking out on what this other thing was that I do run it once in a while. Okay. Maybe that's the issue. Sorry, I'm doing this off screen, aren't I? Yeah, we had MAMP open. I've got several I know don't run anymore. Okay, well, I guess we'll stick with this for now. Oops. I used to use BB Edit a long time back. Had a friend that worked there. I don't know what happened to him. I hadn't talked to him in a while. All right, well, this'll do. Okay, let's see. Where are we on? Well, let's keep our to-do out too. What did I just do? Okay. Hello World in Assembler. Here it is. Okay. Simple xUnit. Well, I don't know. We might be a step away from that. Well, what's weird to me, the way our interpreter is probably going to be, I don't think we will. I don't think it'll use the normal procedure linkages because we're kind of running the thing with this threaded approach is like when every block of code finishes, it just sort of bounces back to the correct routine in the interpreter. So you run a bunch of machine code, say a primary, and then last thing it does is bounce back to the interpreter that says run the next step. And you're running a secondary, you get to the bottom, it has a command that says run this, the next bit of the interpreter to go to the next well, to pop this routine and go to the next one down on the stack, But I would like to make some sort of xUnit, and we're gonna modify our hello world. I don't know. Let's see. Well, just some notes here, right? xUnit. It's got to have some sort of test runner. It's got to have some sort of assertions, and it's got to have some sort of reporting. Okay, and I'm willing to do pretty primitive on any of these. But I guess you write a test method and it calls something and then it asserts something and then it reports the result of that. Okay. All right. So I guess I guess the idea will be you create a procedure. I guess you'd say, what do you want to call these? A function, procedure. It's got to be like a normal one, whatever that is. I've got little resources I looked up here and there, so I have some sense of it. Normally, like you pass your arguments in, I think, x0 through x7, and then the caller is allowed to destroy those. So if you want to do something in x0 and call something, you better save x0. And then x8 through 15, I forget. I think that's caller can assume those are free. So if you're using 8 through 15 before, you better save it. And then I think it's, what is it? Is it 16? I don't know. But somewhere above there's a stretch of ones that are caller save. So if they want to use like x20, I think the caller has to preserve whatever you did there. Okay, so the normal thing is you've got parameters. You got a block of parameter registers. You've got registers that the called routine can use. So the caller has to load up the parameters, save any of these, transient registers, and then make the call. And then if it wants to use the higher registers, it's got to do its own saving. All right, this is not a normal procedure call. I know that. All right, so we will. We won't need parameters for a test method, right? So then we'll have the code. We're going to do some sort of call assert. And then we're going to exit normally. Well, or not. Let's just say exit. I could see our assert. I mean, I could see version 1 says when you fail, I just report the failure, and that's the way it goes. Okay, so let's see. I know it's. Well, I don't know if this guy documented all this stuff in the blog. See what other articles he's got. Competitive trade-offs. No. Okay. It's like BL. Okay. Let's say Xcode. Oh no. ARM is for calling sequence convention. Back. Okay. Consequences of violating the condition. Ooh. Right arm 64 code. Okay, this is Apple's documentation. X18 is theirs. X29 must be valid. We're not going to touch that. Data types, yeah, blah, blah. There's a red zone beneath the stack pointer. Okay, so Apple doesn't modify those. Interesting. And so you can rely on them not to change. All right. Pass arguments correctly. Okay. Oh, it's floating is different too. I forgot about that. Passing an argument with 16-bit alignment, 16 byte alignment. You can start on an odd register. Okay. Normally you have to start even. Okay. Yeah. So normally you'd use X0, X1 would be 128-bit thing. Caller must sign extend 32-bit. Okay. Well, this is not the assembly code. Not going to worry about mangling. That's Intel. Okay, not so helpful. I saved a bunch somewhere. Let's see if I can get down to software assembler. Okay. Calling convention GT. That sounds promising. All right. X0 through X7, parameters and return values. X8, indirect result location. Not sure. Probably is a pointer to something. X9 through 15, freely used by you. 16 and 17 are not to be touched. 18 is not touched. 19 through 28, caller saved. And then frame pointer. I think if you you have nested frames going down as your procedures get deeper, and then I think it points back to the previous frame, so you can get to parent level variables. I don't know if it points that back to the one that called you or the one that statically nests you, but somehow it links those back. It won't matter for us. We're not passing variables that way. Okay. Now let's see. Okay. Function calling. No. Oh, okay. Software assembler. Open at new tabs. Let's try this. We can get them all. All right. x86, 84, don't care. All right. OSX assembler. Okay, that could be useful. I don't know how I ended up with. Oh, probably been saving this for a while. Hello World Mojave. Okay, let's see if they did it the same way. Okay, well they called syscall instead of svc0. It's probably it's a synonym, but yeah, they did it the same way, so it won't help us with this. Classic prologues. Okay, yeah. So this goofy thing is some sort of security code thing. Okay. BL is the procedure call. Okay. Yeah, address protection. So they do stuff. They do stuff. There's PCs can run on ARM or run a simulator or something. So they have some things they do to basically they put in a secret code, and if when you're returning the secret code is wrong, then they know you've got something going on badly. Probably somebody trying to write code over your return stack and hack you. All right. I think it's just BL and return then. So BL puts the current, I think it takes the next address, the return, the instruction after the procedure call, puts that on the stack, and then calls the address you gave. Could use the C-test framework. Yes, we could. But I kind of don't want to. I kind of want to have that feeling that we're booting stuff up from pretty bare beginnings. So I'm going to do it the hard way, even though, I mean, we could just go back to Swift if I wanted to do it easy. So, yeah, well, we have to write a procedure at some point. So let's make this one. So, I don't know. We'll keep Hello World as it is for now. Let's make a, whoops. N? Yeah. Let's make this be, let's do unit unit test.s, unit test demo. Okay, and this will be the piece we put together originally. Yeah, it's just for fun. Okay, we know we need some prologue stuff. We got to do. Let's do this. That will not last. Probably we won't want to be the starting point. Maybe we do for tests. I don't know, but we have to have a start then. All right. Okay, I don't think I have to be on the same line. All right. And then, so this is going to be our test runner. I'm going to say branch with linkage to test one. All right. And then we're going to exit. Now, I don't know. I know we have some macro capability, so we'll get it working and then see what happens. Okay, actually, let's take the whole hello world thing. And let's just run that after our test. We'll put this at the bottom. Okay. And then, I don't know if I can reverse indent. Good. Okay. And what was this? It was syscall? That's the abbreviation, I think. We will see. Okay, so now we got test one here. Test one. Well, we're going to do something and then return. All right. Well, what I'm going to do is something very like this. And then we'll get moving. Okay. Let's just do goodbye. Goodbye. ASCII. And then there's a trick, I think. I don't know if I want to do this trick. Goodbye, 7 letters. Okay, 7. Goodbye. Okay, so this, let's see, make files. I think you can do something like this, right? Is it like .s : .o, and then you do this. And somehow you say $0 or something. All right, I'm gonna make this A dot out. It's kind of traditional, but let's see. Yeah, you'd use that for the difference, but we'll save that. Okay, so I'm gonna have to look up make files now. Basic make file. I almost want a make cheat sheet, maybe. I've done it before, so I should be able to do it again. Well, I can do that. Yeah, that's variables. Yeah. Oh, by $0 is the target. $less than is the dependency. Okay. Are they going to tell me how to do? No. Okay, well, let's keep. All right, so we'll say all depends on hello world.o and unit test demo.o. Is that going to be? Okay, I think. Well, it shouldn't be the dot O's. Okay, it should be. All right, so this is dollar. It's the other way around. Dollar O's depend on dollar S's. Yeah, I don't know if how I can strip that out though. Okay, this was dollar less than. No, that's dollar at. Oh, wait a minute. Where's the input file? Oh, same thing. Oh, I'm doing the wrong one. Okay. I'll get there. Dollar at is the target. Dollar less than is the source. Oh, %.o. Okay. Yeah, I knew there was something. Basically, all object files depend on their assembly files, and then the let's do %.out depends on %.o. Dollar at depends on dollar $o. Let's see if we're entry point start. Let's make this. Well, let's take these out briefly. All right. I don't think this works off the top of my head, but maybe it does. We did the ret. Okay. All right, let's make -n minus d. I think that's just telling us. No, I don't need that. Make minus d. No. Make -n. Oh, it is on arg. So it's not syscall, it's svc 0. There is a thing for it, but I don't remember it. All right, let's do make. Fix up, not sufficiently aligned. Oh, yeah, I got to do my align every time. I think fix up is it changes instructions and stuff when it needs to. Let's see. Good one. Oh, no main. I guess the V goes in the linker command. Well, I'm saying minus E start. Linker command failed. Undefined symbols main referenced from initial undefineds. Let's see what we got. Let's try make unit test demo.o. Okay, so symbols. All right, that's okay. LD, make sure that's a tab. All right. Well, we can say minus V, I guess. CC unit test demo minus O. Well, who's running unit test demo? Oh, I didn't make these outs. So I think it's trying to run it as a C program. Okay, that's that minus V. It's so complete, I don't know if it works or not. Wrong. Oh, we didn't clean those. Make clean. Wow, okay. Mig. Okay, so we run our unit test demo. We expect hello, goodbye. Oh, goodbye, hello. Oh, I guess that's right. Okay, we can make it better. Okay, so I wanted to know before. Well, let's put a hello world down here. We'll move this one up. Okay, I think this will work. It's a little sloppy looking. I'm gonna have to work on make file. RM. There's a command, or we can. There's something that'll let us do it if it's not there. I'll delete. Well, how am I doing here? Let's see. RM star.a. I don't have any star.a's. No matches found. No such file directory. Well, isn't that weird? Do not display a diagnostic. Minus F should do that. Oh, make files. How do I specify my arguments? Is it this? Oh, I guess $arrow. No, that forces him to build first. Ha, okay. Okay, I think we're okay. All right. Okay, so we got a test. We need an assertion. Right. So let's get these things. Okay, so let's make a new routine. Add. I'm going to say the result in x0 should be the sum of x1 and x2. Okay, so you load up two registers, you call this, you will get, well, I think it's just add x0, x0, x1, and return. Okay, well, let's just do sub for now. Okay, so when you call this, the test should put something in x0. Let's do a literal 2, x1, do a literal 5, and then call our method add, branch link add, and then we want to do some assertions. And I guess the assertion, assert equal. Okay. We're going to put expected. Oh, move. We'll put the expected in x1. Sum should be 7. Assert equals, and then return. Okay. Print a message if x0 is not equal to x1. Okay, so compare. Let's see, loading. I don't think I care about that. They're calling C printf. Well, let's look for arm compare method. Compare. Well, I really want a branch. Um, compare, and you can do less than, right. Compare. Well, we know we want to do a compare. X0 to X1. And then, I don't know, there's a branch. Well, this is thumb. That's not really the version of ARM we're using. No. Branch not equal. Okay. If it is equal, we want to return. I've got to find a way to turn that off. Okay. All right, and if you don't equal, I'm going to print. FAI, LID, and 7. Yeah, yeah. So, did I say R1? I think R is the generic name for the register, and then X's are 64-bit integers, W's are 32-bit. Um, I forget the rest. I think there's a V is maybe 32-bit float or something, but the type is kind of embedded into the register name. So I don't think you normally say R whatever. It's there, but there is another label you might use. I'm pretty much going to stick to 64-bit stuff. I'm not going to worry about data types in our little language. I'm not even going to worry about floats, at least to start with. Okay, so what I want to happen is I want you to return if they're equal, then just return. If they're not equal, then we're just going to print failed, and eventually we'll get able to print the values. Okay. So let's get our test. So the test is check 2 plus 5 equals 7. We'll call assert equal on that and return. And I don't think I need this stuff anymore, except the exit. Okay, so the whole thing is run test one, call exit. We don't need hello world. Okay, and test one is our addition test. Here's our add method, which is going to fail. And here's our assert method. So I think we'll see this. Not a lot to start with, but something. Okay, we don't need goodbye either. Okay. Oops. Okay, so make should just do make all and only hello world. Oh, I deleted things, so hello world's not there. All right, and I should be able to run unit test demo. Failed. Good. I don't know why it's taking so long. What's going on? Yeah, I mean, I think it'd be good to have the test name embedded too, but something's not right. All right. Branch test one. Okay, so we call test one. It does some stuff. Oh, failed. No, that just prints the message. That just kept running. I thought I called. Yeah. Okay, let's make sure everybody's returning. Okay, so he returns, that returns. We know that does because we got there. Test one returns. We know it does. We don't know it does. But it should have got here. Use 0 return code x16, x00, x16, service 0. x00, pound 1, service 0. Make sure I did the pounds. Yep. I don't. Already, I'm not seeing it. Yeah, I subtracted. So failing is right, but it should just fail and then stop, and it did not. It appeared to just hang. I don't know if it's what it's doing. All right, let's. Gosh, I can put this various places, but okay, let's take this out. I'm not sure if it apparently uses slash slash. All right, so now save that. Now my function is all it's doing is exiting. It should just exit. Let's see if it does that. Whoops. Make. Yeah. Okay, that exits. So branch L test one, move registers, branch and link add. I don't think I have to do anything besides that BL. All right, but we're gonna work our way through. Actually, there is it LLDB? I don't know what the name is. Dot. Oh, it's gonna exit. Okay. I make sure it comes back from its branch and add first. Wait. Oh. I don't know why the RM. I guess I should take this out, let it hang. Okay. I don't want that. Okay. Now, if I control Z, I can PS. I don't know if that's, I mean, that's the PID. Okay. Okay, we loaded a program. You can attach to a process. Okay. Stop. Signal stopped. Okay, so I guess it's stuck at the return. I guess it's giving us a little context. So it's the return before the sub. Return before the sub. So why are you having trouble? I mean, we're not changing. Assert equal doesn't change anything, does it? It doesn't compare, it does a branch, it returns, or it prints and returns. We're missing return line 11. Well, I mean, it's calling exit, but you're right. There's no return there. Sorry. We can see. Okay, let's quit this. C, C, PS. Is it -9? Yeah. Okay. Make. Oh, shoot. Yeah, I mean, so I don't know if we believe the LLDB, but I think it's saying it was frozen here at return. Um, hey Tooks, yeah, we're trying. Okay, I guess I got to find something to make sure I understand BL and RET is all you really need to do. Um, it, ARM64 procedure call. This is probably accurate. Okay, well, they're doing a line 4s. If that's comments, I guess. They push, they add, they move, they BL, add pop. Global main. Well, this is weird. He has no return there. Push pop. Right. That pushes arguments on the stack. Yeah, the link register, that's all implicit. It's a Windows thing. Cool. I don't think this one's going to be too helpful. We can just do man AS if we need to. That's the make file stuff. ARM64. I know we had a calling convention that I don't think we'll need for a while. No, not calling convention. We had one that did some calls. That's not even, I don't even think that's ARM code. No, it's not. Yeah, I mean, I just thought it'd be nice change of pace. I always wanted to try this threaded interpreter. I'm getting balled up on very much basic stuff, but we'll see. Okay, ARM64 procedure call example. I thought we had one that showed, I think, not this guy, this one. Loading addresses. He's got a whole series. Now this one will need two register modes. Well, let's skip forward. Okay, I need to catch these at some point because to make sense of the assembly code, you really want to use those. I think it was like episode 11 or something. Ugh. Maybe this will show us something. These documents, I don't know, they're kind of painful. Now we don't set that frame pointer. I don't know if that's getting us. We don't do anything with it. Yeah, we're not getting anything about how to actually do it. His pop BL, where's his return? I guess that's his pop. Oh, R4PC, yeah. Okay. Yeah, that's not you can just say return though. I'm 99% sure. Right, you do stuff and then you read. Yeah, read is move XP. That's the link register. Right, so when you do a call, BL, you're saying write the my address plus the get to the next instruction from here, put that in the X30, which is the link register, and then jump to wherever I said, and then return should just be copy the link register back to the PC. Yeah. Right. Developer arm. Yeah, it just is not helpful. Return address protection. This, we had this one open, I think. It's that Packibs. He had a nice article that was like, oh, here we go. Classic calling convention. It's just so many rules. That's the float stuff. Oh. Getting further and further away. Yeah, I mean, you can, well, because of the registers, right, you might want to, you might have ones you have to save because your procedure touched them. And so, they were caller save registers. So they would save them at the beginning of the routine typically, and then at the end, pop those registers back on. And popping PC is sort of being a clever way to get PC too, because that got pushed as well automatically. All right. But okay, hopefully this is RV8. I don't know if that's the same. Well, there's red. Yeah. Okay, you can manipulate the stack. Yes. They don't show the call. Load, register, store, move, add, sub. Yeah, that's kind of how much I know. Stack goes down. Yeah, okay. Ugh. So, okay, maybe I just got to work through. So when we did this right here, it failed. It exited. Let's do this here. I do it after the add, before the assert. Okay, so Okay, what do we got going here? Let's make unit test demo.out. I don't know why I'm getting that RM. It's clean, not. Oh. I don't think it should matter that it's there. Oh, he's not indented or outdented. Okay. Let's try that again. Yeah. Try to make clean again. Oh, I still get that. Okay. But I have unit test demo here. Okay, so it's exiting before it does anything. Now I'm going to do it after the assert. So this is after the print. Oh, weird. Okay, so this return. Assert equal comes back, and all it should do is return. I'm very puzzled. This return test1 should come right back here and exit. Okay, what the heck? All right, let's make assert equal simpler. All it's going to do is return, and then a bunch of junk it's never going to get to. I don't know why this should be needed. I mean, we only got, what, 20 instructions here? What the heck? Okay, so it fails if all it does is return. I guess I can we comment out? No. Okay. Yeah, so exit is this. So basically it's command the one is the Unix calls the Unix exit call. And 0 is saying it returns successfully. All right, and this is just the call. But the add did return. Because we came back from add, and then we could fail there and exit there. And then we said come back from assert equal. Okay, I'm just going to do some junky thing. And it seemed to hang. Pop the PC once before returning. I don't think so. Return is pop PC. I think. Let me Let's find an explanation. Code walkthrough. Okay, here's his demo. This guy's has good writing about it. Okay, move FP to SP. Now, maybe I'm trying to shortcut too much. We don't need any stack variables, so there's no reason we need to do this stuff. He's modifying X19, X20, and SP. Storing X21 on the stack. He's pushing the frame pointer on there and move the stack pointer to the frame pointer, so he's getting the current one. We shouldn't need any of that stuff. I mean, my argument would be stronger if it was working, I grant you. All right, where's his ending? Here's return. Well, he does those, but notice he's not doing a load P to return. Jump back to the address in LR. And then his better version. Okay. I got to figure this out. Should exit if the assertion fails. I would say yes. It's okay. Let's try it that way. So I'm going to put a copy of this down there. I almost think we got to figure out macros too. But okay, so there's a print and an exit. Well, let's see what our return codes are. So Mac OS, well, Unix return codes. I forget, it's 0 successful and anything else is, yeah, errors. We don't worry about even or odd. Okay, so if we return 1, failed. Excuse me. Okay, take this back out. All right, we're going to compare the two registers. If they're not equal, we go down here to failed. I don't think the syntax cares about this. So let me do it that way. We'll jump to failed, and we have the failed message. Count the characters 3, 6, 7. That's correct. X16 is 4 is right, and that's standard out. Source code 1. Return I don't think is needed because I don't think it can run once. I think exit just terminates the whole process. So I don't think you even really need that return. But so this should run test 1, compute the sum, which should be 7, moves that to the expected, branches to assert equal. And we got it wrong because it's doing subtract instead of add. If it's not equal, then markdown failed, and then we print failed and exit. Okay. Take that. So it's the returning that throws it off. Okay, this is so crazy. All right. So it doesn't really return because this really does kill the process. So if I take this out, I mean, if I moved it to after here, right, it should have returned from it, and then it should do the exit code. I don't know if something between the two calls, maybe, I mean, I may misunderstand this thing, but like I think frame pointer should start out good and we don't touch it, so it shouldn't matter to us. But oh, what is going on? So maybe it's this fail. This one's failing. Okay, so now I took it out of test one. I mean, test one should come back, return back to here, and then exit. No, it's not. So I don't know. We're due for a break, I think. Let's take a break, see if it runs when we get back. What I'm getting the feeling is I'm messing up something in the return of this thing, so I would think it would have to get here. But something's wrong between this. I would think when you call this, the return should be pointing at this instruction, and the return should restore to here, which should maybe I'm not pushing something. All right, we're taking a break. See you in a few minutes. All right, I have a theory. I think I'm wrong on BL, and I don't think this explained it, but I think what's going on is BL puts the link register, gives it the address of the following instruction, and then RET takes the link register and puts it in the PC, and so returns us to the following instruction. I think what I've done, though, I think this is back to the thing for popping. I think we need to do some pushing and popping, because what I think happens is we come in here, we come in test one. I think we are destroying the link register and not able to get back 2 levels is the deal. So blink BL add gets us back to here, but the link register is on assert equal. I don't know if I'm filling up my stack or not, but the link register, we call BL add, the link register value was this address originally, and then line 8, and then it became 20. All right, and so we came back, we returned to 20, fine. It becomes 21, we come back and return here, but the link register is still pointing at assert equal, and so I think it's trying to return to our assert equal method, and it's just freezing up because of that. So I think we do need to do a push. Service 80 for the M1. We'll have to look up this SVC called. Okay, ARC64. Immediate operand has no role in determining the vector. It's always obtained from that. Okay. operator stored. Yeah, I don't think it's doing anything with that. I think service 0 is just service anything, from the sound of this, one answer on Stack Overflow. But I think the push pop thing maybe is I think we need to push LR and then pop it. All right, let's see if this makes sense. All right, and then push looks like, oh, it's just push. Okay. So because, yeah, if we were a leaf method, we wouldn't need to do this. This is because we're not a leaf. Okay, so I think I need to do push LR. Because the link register is set in here. I'm mutating it here, which is fine. He changes it to here. He calls assert equal. He changes it to here, and then we're just recycling the ret. Okay, and then pop. I don't know if it's just pop LR. I want to do the minimal thing and make sure I understand. Now he's popping it to PC. I guess if you pop it to PC, it's going to return. And I think ret is probably an abbreviation for that. Push and pop the IP register. Oh, yeah, procedure call stack has to be 64-bit aligned. So I think I'm going to be 32-bit aligned. No. I think 8 bytes, right? 64-bit. It should be okay. I think the standard might require it to be 128-bit aligned, though. Okay, so let's check the theory here. So because we're not a leaf, we need to save the LR that gets us back up here. We can make one level deep calls. We're calling leaf procedures. When they get back, we need to pop LR, so LR has the value pushed on the stack, which is this return. Okay, so it's a theory. Boop. Error vector register expected. Now, what was their stuff? Push. Well, what the heck? They're doing a line 4. What's that message? Error, unknown token, invalid operand, error, vector. Wow. Oh, is it PSH? No? Okay. It's 16 byte aligned. So you need to preserve LR, which is actually X30 is LR. Yeah, you can return from any register. SP must be 16 byte aligned. Okay, so let's push another register. I don't know. This seems to be a syntax complaint. BXLR. Yeah, I think BX is a indirect branch. So if you indirect branch through the LR link register, you're saying return you branch to the address stored in this register. But you got to make sure that register is right. Now I don't know if this. Let's push X20. All right, and these are leaves, so they don't care. Okay, that's my theory. But I don't know. The syntax seemed to work for that guy, and it's oops. Make vector register expected. Well, I mean, I can do these stack things, but I could have sworn. Where's this guy's stuff? Oh, the multiplication division. I'm looking for this one. Nope. Oh, there's all your other registers, though. Here's your X's, your 32-bit floats or V's. Here's a stack pointer. Callee saved. Okay, so X20 was a good choice. Where's that push instruction? Maybe we do have to do the stack arithmetic. Yeah, we'll do this. Okay, so this is like a post increment, but we're doing it 16 bytes, which is the stack alignment they want, and then it's LDAR right the other way. Except we don't want X0, but we want LR. Okay. Yeah. Okay. And let's see if this works. Thank you. All right. And then this should be an add. All right. Now let's play with it. Okay. So can we call BXLR to return? And I think so, because now the link register has the right return value up here. Now I probably should figure out how to get LDB running. Whoops. Oh, they don't like it. No. That should be okay. No, there's definitely an indirect branch. We're going to need it, so I want to make sure I know what it is. ARM64 indirect branch. Maybe they just branch with brackets or something. No, they want BX. I suspect it's a Mac assembler versus GNU assembler. BR is like bridge. Okay. ret is analogous to BR. Yeah, it gives a hint. Well, let's see if this says anything useful to us. My record is not good. Okay. But, best practice guide, huh? Like whose practices? Yeah. Okay. I don't know which one we have. No, that's not going to help. Okay, what was this? Still loading. All right. Branch. Maybe just BR? BXLR, BL should store the link. Yeah, BL stores the link address. It stores the address of the next instruction in the link register. And then when you're moving that, basically the return, I believe, let's see if this one works. I think BR can take the register. Yeah. Let's see if it works. Whoops. Yeah. Okay. So I don't know if ret is a return. I mean, if it maps to exactly this instruction or not. If you do multiple BL calls to stash LR, no, I think that's the mistake I was making. So if I take this out and take this out, and I'll put this back to ret, but I think ret is the equivalent of this. But when we want to branch to some other register, we can say branch X1 or something, whatever there. Okay, I'll make this ret again. Okay, so I think what happens is BL test 1 says, first I'll set link register to the next instruction, so line 8, and then I'll set the PC to test 1. So it goes down to test 1. Link register is 8. It comes down to BL add. It says, okay, I'll set link register to 21 and jump to the add routine. It returns, comes here, because 21's where the link register was, and says, okay, BL is cert equal. I'll set the link register to 25, because that's where the next line, and I'll jump to assert equal. Okay, and he does that, and he comes back. Now he says, I want to return, which is BR LR. What's LR? Well, it's still 25. So I think what was happening was my return was looking at LR and saying, oh, LR is 25. You should go to line 25. Go to line 25. Go to line 25. Okay, so it does not stash them between calls. Now, the problem, the reason this routine's a problem and not these guys is because these are leaf routines. They're not calling anybody else. And so they don't muck with the LR. And so whatever it got set to stays back. But this one was not a leaf routine. And so whenever the things it called messed with the LR, then it does its return. It's not right. It's going back here. Now, what would be interesting, did we put a print here? I'm going to try putting the print there. Okay. After, let's see, after this, before the return. Okay, so we're saying print failed message, and I'll just say, how about here message? And let's put here message ASCII 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay, just don't have to change anything. All right, and make that, run that. I expect it to fail, and I'm hoping it prints. No. Okay. Well, I'm not sure if that means I don't fully get it. Okay, it comes, LR should be that. I thought it would come here and print and print and print. Okay, well, I think I'm not going to worry about it. We'll take this for now. Make sure we're working. Whoops. Yeah. Make, run. Okay. Push R4 on. Yeah, I think that's correct. R4 is just well, there's no real reason to push R4 per se. I think they're just pushing two things. Yeah, let's well, let me push this first. Okay, I'm gonna have to write a command for that, I guess. I think okay, yeah, I don't know why the push instruction is not showing up for the Mac assembler. Okay, but the reason they're pushing two things is the stack has a requirement that it moves by 16 bytes, not 8 bytes. So 8 bytes is 64 bits, right? So that's one register's worth. So they have to push two registers. And I suspect, at least, if they're doing it by default R4, then it's really just pushing R4 just to have something else to push to make sure everything lines up. Because if you just did push one thing, I mean, if I change this to 8, -8, whoops, and -8 here. Okay, so if we said, well, gee, the buffer is only, or sorry, the register is only 8 bytes wide. Let's just take up 8 bytes on the stack, and then we got more on the stack. So I want to see how this fails, because I suspect we'll make this mistake again sometime. So assuming it does fail, but I'm hoping we get a crash out of it. Yep. All right. So let's do undo. Good. All right. Okay. Oh, being stuck for half an hour on something stupid, but that's the way it goes. I'm learning. All right. So I think I kind of have something here, right? I've got this assert equal function. If you call it with two registers, if you call it with actual and expected, basically. A little bit backwards, but return values are always x0. So, non-floating point returns are always x0. So I think it makes sense to do that order. All right. So now, yeah, let's get a little fancier. All right. So, I would like to I would like to print the values, right? Um, let's see. Um, yeah, I'd like to say failed x0. Well, we'd like to know the routine name too. Hmm. Yeah, maybe the pass, like pass fail kind of thing. Maybe you should pass in a message. Hmm. We'd like to know which test was passing and which failed. And even if it was just listing, you know, test add, passed, test fit, whatever, I'd kind of be okay. And I kind of am okay if we start using ASCII Z, but it's going to take more work. Um, yeah, maybe it's time to figure out macros. Let's see. So Mac assembler macros. I can try the GNU ones and see if they work. CPM one. Okay, thanks. Right, that's not relevant. Well, maybe I could say Mac AS macros. This is probably not the right kind. No. Okay, I should keep assembler in this search. Well, how about ARM64? That's hardware level. Well, let's see if we can find GNUs. Oh, I saw something. What did I see? It was I think a message we had today was something about macros. I don't know how far back this will go. Well, it's like PFX or maybe it's that minus V. This is not so helpful. Well, it's chatty enough. That's coming from make, not from assembler. Yeah, this is what I'm looking for. That's LT. That's not going to do it. Okay, let's try man as. Okay, there's a preprocessor stage you can turn off that has macros somewhere. So that means it must be on if we can figure out how it works. Um, Macros. Okay. Well, let's just try it. They may have supported the same thing. Sum from equals 0. That's the name. Oh, then the arguments. Okay. Macro. Well, I guess I should put it earlier. Okay. Well, macro. Let's call one for exit. And at the end, we'll do endim. I should probably put this above. Okay, move this. All right, let's put the macro here. I assume we just call it like this. Macro long sum 05. Okay, let's see what it thinks. Didn't complain. Haha. I think we're good. Okay. Let's make a macro print. That's down here. With a message and a length. Okay. Well, let's just try it up here. Right here, message 7. I guess failed message 7 and exit. Okay, just a quick test. ASCII place to. I kind of think it might. Some assemblers are very strict about there are data partitions and code partitions. I think it may pull those into a data partition. Not sure how we can figure out. But I mean, it seems like we're putting it in this. I'm not sure. I'm going to run this. It should print failed. And that would mean our macro was kind of working. No. Fix up kind. ADR move. Unknown arc. Fix up. line. Oh, instantiation. Okay. Unknown arc64 fix ADR X1 message. ADR. Does that even seem right? Why doesn't it move register? ADR X1 message. Oh, maybe you have to do something else in the macro to get them. Yes, you do. Backslash. Okay. I don't know why ADR though. All right, and then let's do a different one just to make sure. So the length is 5. The message is here. Message. I bet I can put the. I bet I can do that. Oops. I'm hoping I can do that. I know I'm changing 2 things. All right. But that makes me more confident that we're doing the right thing. Okay. Macro take a string and define the ASCII block to print. Ooh, that's a good question. Let's try it. Well, let's check these in first. So, trying out macros. I think I can do this. All right. Yeah, so let's take the message. We're going to put ASCII message. Right, but then it's going to have to, I think maybe then align to. Oops. Try to put this at the end. At some point, this becomes more than a macro, you know, but I don't think there's a big harm. Okay, so we're going to try moving address. Well, we would have to specify relative address. Do you think that's reasonable? Unless, can we put this in the macro too? Just colon. There must be some way to generate, yeah, the counters. How many macros are executed in this? You can copy that to your output within a macro addition. Back at. I don't know if you can pass a string in directly. Let's try it. Print testing, which is 7, and exit. Okay. While in macro. Oh, maybe I just had to put the quotes in. Let's see. /new test demo. Illegal hardware. Illegal hardware. I wonder, that almost says you can't. It's like it's executing it. But we can keep going. I'm not sure it's worth all this, but we're learning. Skip around it. Invalid operand. Invalid operand. Why is that invalid? Operand. Oh, exit. Didn't mind that. Yeah, I don't know if we have something like that. And I don't know, is there a no op? Just to kind of keep it internal. That's our print. Jump to exit whatever. Is BR even the right branch? I'd have to check. Embarrassingly, but sorry, let me save. Unknown directive. BR. Let's make sure about this. ARM64, okay. Just B. I guess BR is branch register, BL is branch link. Okay. Hey, promising. All right, I don't know what testing percent is. Let's see. Take this pipe to OD minus C. D is ding. 4, 5, 6, 7. Okay. Why is that a problem? That's the length. There must be a way to get the expansion. Dot text directive. Yeah, so there are sections. Save non-global defined labels beginning with an L. Yeah, we're using the C lang. Oh, maybe I should be looking at that. Run the preprocessor stage. Let's try that. Minus E. I don't know what it does with it. They still document it as Mac OS X, and they made us change it. Code generation, no. Pass arg. Diagnostics. Okay, I guess I could say like clang show preprocessor output. I don't know if that's that. Dumping preprocessor state. Only run the preprocessor. Let's try that. Okay, so we gotta look at our make file. And just AS. Oh, let's just try AS. No. No, because in the Unix level, they're right. They just take the string and the length. I think the extension we should do, I would like to just have it take ASCII Z's, and then we can build up C style strings and let it print those. How are we doing on time? Oh, we're out of time. Okay. Well, I don't know how to dump macros, but they are doing something for us, so I'm liking it. I kind of feel like this really should be a print method and not a macro, but the exit, that's kind of okay. Right, so we'll take this out. Okay. Yeah, I think yeah, I still don't know what that percent was. Is that my Oh, maybe it's picking up that. I don't know. I don't know what that percent was though. Um, we'll make this again one last time and run it again one last time. Yeah, we're getting something. We'll have to see. I really would love to see what that macro output is. Yeah, I mean, there must be something. ASCII, we put the message in here. I don't know. Well, we'll pick up there tomorrow anyway, 2 to 4:30 Eastern or 7 to 9:30 p.m. UTC. I would love to find a way to dump these macro, the results of the macro expansion and see what the actual stuff we're getting. But I think my plan for tomorrow is I want to get, I'd like to make a print subroutine that takes zero terminated strings and use that in the assert to have it print something like failed x0 equals this, x1 equals that, or actual x0, x0, x1. Print that in the message. Maybe have a print numeric so it can dump those, maybe as hex. And I think that'll give us a reasonable starting point to do some real work. But yeah, I mean, a lot of looking stuff up and all that. But I think we've solved a few things like this stuff, and it'll be a little quicker tomorrow, I hope. All right. Well, have a good evening and take care. See you tomorrow, I hope, or another time. Bye-bye.